Wind is the flow of gases on a large scale. On the surface of the Earth, wind consists of the bulk movement of air. In outer space, solar wind is the movement of gases or charged particles from the Sun through space, while planetary wind is the outgassing of light chemical elements from a planet's atmosphere into space. Winds are commonly classified by their spatial scale, their speed, the types of forces that cause them, the regions in which they occur, and their effect. The strongest observed winds on a planet in our solar system occur on Neptune and Saturn. Winds have various aspects, an important one being its velocity, another the density of the gas involved, another is the energy content or wind energy of the wind. In meteorology, winds are often referred to according to their strength, and the direction from which the wind is blowing. Short bursts of high-speed wind are termed gusts. Strong winds of intermediate duration are termed squalls. Long-duration winds have various names associated with their average strength, such as breeze, gale, storm, and hurricane. Wind occurs on a range of scales, from thunderstorm flows lasting tens of minutes, to local breezes generated by heating of land surfaces and lasting a few hours, to global winds resulting from the difference in absorption of solar energy between the climate zones on Earth. The two main causes of large-scale atmospheric circulation are the differential heating between the equator and the poles, and the rotation of the planet. Within the tropics, thermal low circulations over terrain and high plateaus can drive monsoon circulations. In coastal areas, the sea breeze, land breeze cycle can define local winds. In areas that have variable terrain, mountain and valley breezes can dominate local winds. In human civilization, wind has inspired mythology, influenced the events of history, expanded the range of transport and warfare, and provided a power source for mechanical work, electricity and recreation. Wind powers the voyages of sailing ships across Earth's oceans. Hot air balloons use the wind to take short trips, and powered flight uses it to increase lift and reduce fuel consumption. Areas of wind shear caused by various weather phenomena can lead to dangerous situations for aircraft. When winds become strong, trees and man-made structures are damaged or destroyed. Winds can shape landforms via a variety of aeolian processes such as the formation of fertile soils, such as loess, and by erosion. Dust from large deserts can be moved great distances from its source region by the prevailing winds. Winds that are accelerated by rough topography and associated with dust outbreaks have been assigned regional names in various parts of the world because of their significant effects on those regions. Wind also affects the spread of wildfires. Winds can disperse seeds from various plants, enabling the survival and dispersal of those plant species, as well as flying insect populations. When combined with cold temperatures, wind has a negative impact on livestock. Wind affects animals' food stores, as well as their hunting and defensive strategies. Causes of wind. Wind is caused by differences in the atmospheric pressure. When a difference in atmospheric pressure exists, air moves from the higher to the lower pressure area, resulting in winds of various speeds. On a rotating planet, air will also be deflected by the Coriolis effect, except exactly on the equator. Globally, the two major driving factors of large-scale wind patterns are the differential heating between the equator and the poles and the rotation of the planet. Outside the tropics and aloft from frictional effects of the surface, the large-scale winds tend to approach geostrophic balance. Near the Earth's surface, friction causes the wind to be slower than it would be otherwise. Surface friction also causes winds to blow more inward into low-pressure areas. A new, controversial theory suggests atmospheric gradients are caused by forest-induced water condensation, resulting in a positive feedback cycle of forests drawing moist air from the coastline. Winds defined by an equilibrium of physical forces are used in the decomposition and analysis of wind profiles. They are useful for simplifying the atmospheric equations of motion and for making qualitative arguments about the horizontal and vertical distribution of winds. The geostrophic wind component is the result of the balance between Coriolis force and pressure gradient force. It flows parallel to isobars and approximates the flow above the atmospheric boundary layer in the mid-latitudes. The thermal wind is the difference in the geostrophic wind between two levels in the atmosphere. It exists only in an atmosphere with horizontal temperature gradients. The ageostrophic wind component is the difference between actual and geostrophic wind, which is responsible for air filling up cyclones over time. The gradient wind is similar to the geostrophic wind but also includes centrifugal force. Measurement. Wind direction is usually expressed in terms of the direction from which it originates. For example, a northerly wind blows from the north to the south. Weather vanes pivot to indicate the direction of the wind. At airports, windsocks indicate wind direction, and can also be used to estimate wind speed by the angle of hang. Wind speed is measured by anemometers, most commonly using rotating cups or propellers. When a high measurement frequency is needed, wind can be measured by the propagation speed of ultrasound signals or by the effect of ventilation on the resistance of a heated wire. Another type of anemometer uses pitot tubes that take advantage of the pressure differential between an inner tube and an outer tube that is exposed to the wind to determine the dynamic pressure, which is then used to compute the wind speed. Sustained wind speeds are reported globally at a 10 meters height and are averaged over a 10-minute time frame. The United States reports winds over a 1-minute average for tropical cyclones, and a 2-minute average within weather observations. India typically reports winds over a 3-minute average. Knowing the wind sampling average is important, as the value of a 1-minute sustained wind is typically 14% greater than a 10-minute sustained wind. A short burst of high-speed wind is termed a wind gust. One technical definition of a wind gust is the maxima that exceed the lowest wind speed measured during a 10-minute time interval by 10 knots. A squall is a doubling of the wind speed above a certain threshold, which lasts for a minute or more. To determine winds aloft, Rawlinsons determine wind speed by GPS, radio navigation, or radar tracking of the probe. Alternatively, movement of the parent weather balloon position can be tracked from the ground visually using theodolites. Remote sensing techniques for wind include SODAR, Doppler lidar and radars, which can measure the Doppler shift of electromagnetic radiation scattered or reflected off suspended aerosols or molecules. And radiometers and radars can be used to measure the surface roughness of the ocean from space or airplanes. Ocean roughness can be used to estimate wind velocity close to the sea surface over oceans. Geostationary satellite imagery can be used to estimate the winds throughout the atmosphere based upon how far clouds move from one image to the next. Wind engineering describes the study of the effects of the wind on the built environment, including buildings, bridges and other man-made objects. Wind force scale. Historically, the Beaufort wind force scale provides an empirical description of wind speed based on observed sea conditions. Originally it was a 13-level scale, but during the 1940s, the scale was expanded to 17 levels. There are general terms that differentiate winds of different average speeds such as a breeze, a gale, a storm, tornado, or a hurricane. Within the Beaufort scale, gale force winds lie between 28 knots and 55 knots with preceding adjectives such as moderate, fresh, strong, and whole used to differentiate the wind's strength within the gale category. A storm has winds of 56 knots to 63 knots. The terminology for tropical cyclones differs from one region to another globally. Most ocean basins use the average wind speed to determine the tropical cyclones category. Below is a summary of the classifications used by regional specialized meteorological centers worldwide. Enhanced Fujita scale. The Enhanced Fujita scale rates the strength of tornadoes in the United States based on the damage they cause. Below is that scale. Station model. The station model plotted on surface weather maps uses a wind barb to show both wind direction and speed. The wind barb shows the speed using flags on the end. Each half of a flag depicts 5 knots of wind. Each full flag depicts 10 knots of wind. Each pennant depicts 50 knots of wind. Winds are depicted as blowing from the direction the barb is facing. Therefore, a northeast wind will be depicted with a line extending from the cloud circle to the northeast, with flags indicating wind speed on the northeast end of this line. Once plotted on a map, an analysis of isotachs can be accomplished. Isotachs are particularly useful in diagnosing the location of the jet stream on upper-level constant pressure charts, and are usually located at or above the 300 hectopascals level. Wind power. Wind energy is the kinetic energy of the air in motion. The kinetic energy of a packet of air of mass m with velocity v is given by half a meter v2. To find the mass of the packet passing through an area A perpendicular its velocity, we multiply its volume after time t has passed with the air density ρ, which gives us m equals avt ρ. So, we find that the total wind energy is differentiating with respect to time to find the rate of increase of energy. We find that the total wind power is. Wind power is thus proportional to the third power of the wind velocity. Theoretical power captured by a wind turbine. Total wind power could be captured only if the wind velocity is reduced to 0. In a realistic wind turbine this is impossible, as the captured air must also leave the turbine. A relation between the input and output wind velocity must be considered. Using the concept of stream tube, the maximal achievable extraction of wind power by a wind turbine is 59% of the total theoretical wind power. Practical wind turbine power. Further insufficiencies, such as rotor blade friction and drag, gearbox losses, generator and converter losses, reduce the power delivered by a wind turbine. The basic relation that the turbine power is proportional to the third power of velocity remains. Global climatology. Easterly winds, on average, dominate the flow pattern across the poles. Westerly winds blow across the mid-latitudes of the Earth, polewards of the subtropical ridge, while easterlies again dominate the tropics. Directly under the subtropical ridge are the doldrums, or horse latitudes, where winds are lighter. Many of the Earth's deserts lie near the average latitude of the subtropical ridge, where descent reduces the relative humidity of the air mass. The strongest winds are in the mid-latitudes where cold polar air meets warm air from the tropics. The trade winds are the prevailing pattern of easterly surface winds found in the tropics towards the Earth's equator. The trade winds blow predominantly from the northeast in the northern hemisphere and from the southeast in the southern hemisphere. The trade winds act as the steering flow for tropical cyclones that form over the world's oceans. Trade winds also steer African dust westward across the Atlantic Ocean into the Caribbean Sea, as well as portions of southeast North America. A monsoon is a seasonal prevailing wind that lasts for several months within tropical regions. The term was first used in English in India, Bangladesh, Pakistan, and neighboring countries to refer to the big seasonal winds blowing from the Indian Ocean and Arabian Sea in the southwest, bringing heavy rainfall to the area. Its poleward progression is accelerated by the development of a heat low over the Asian, African, and North American continents during May through July, and over Australia in December. Westerlies and their impact. The westerlies or the prevailing westerlies are the prevailing winds in the middle latitudes between 35 and 65 degrees latitude. These prevailing winds blow from the west to the east, and steer extratropical cyclones in this general manner. The winds are predominantly from the southwest in the northern hemisphere and from the northwest in the southern hemisphere. They are strongest in the winter when the pressure is lower over the poles. and weakest during the summer and when pressures are higher over the poles. Together with the trade winds, the westerlies enabled a round-trip trade route for sailing ships crossing the Atlantic and Pacific Oceans, as the westerlies lead to the development of strong ocean currents on the western sides of oceans in both hemispheres through the process of western intensification. These western ocean currents transport warm, subtropical water poleward toward the polar regions. The westerlies can be particularly strong, especially in the southern hemisphere, where there is less land in the middle latitudes to cause the flow pattern to amplify, which slows the winds down. The strongest westerly winds in the middle latitudes are within a band known as the Roaring Forties, between 40 and 50 degrees latitude south of the equator. The westerlies play an important role in carrying the warm, equatorial waters and winds to the western coasts of continents, especially in the southern hemisphere because of its vast oceanic expanse. Polar easterlies. The polar easterlies, also known as polar Hadley cells, are dry, cold prevailing winds that blow from the high-pressure areas of the polar highs at the north and south poles towards the low-pressure areas within the westerlies at high latitudes. Unlike the westerlies, these prevailing winds blow from the east to the west, and are often weak and irregular. Because of the low sun angle, cold air builds up and subsides at the pole, creating surface high-pressure areas, forcing an equatorward outflow of air. That outflow is deflected westward by the Coriolis effect. Local considerations: sea and land breezes in coastal regions. Sea breezes and land breezes can be important factors in a location's prevailing winds. The sea is warmed by the sun more slowly because of water's greater specific heat compared to land. As the temperature of the surface of the land rises, the land heats the air above it by conduction. The warm air is less dense than the surrounding environment, and so it rises. This causes a pressure gradient of about 2 millibars from the ocean to the land. The cooler air above the sea, now with higher sea level pressure, flows inland into the lower pressure, creating a cooler breeze near the coast. When large-scale winds are calm, the strength of the sea breeze is directly proportional to the temperature difference between the land mass and the sea. If an offshore wind of 8 knots exists, the sea breeze is not likely to develop. At night, the land cools off more quickly than the ocean because of differences in their specific heat values. This temperature change causes the daytime sea breeze to dissipate. When the temperature on shore cools below the temperature offshore, the pressure over the water will be lower than that of the land, establishing a land breeze, as long as an onshore wind is not strong enough to oppose it. Near mountains over elevated surfaces, heating of the ground exceeds the heating of the surrounding air at the same altitude above sea level, creating an associated thermal low over the terrain and enhancing any thermal lows that would have otherwise existed, and changing the wind circulation of the region. In areas where there is rugged topography that significantly interrupts the environmental wind flow, the wind circulation between mountains and valleys is the most important contributor to the prevailing winds. Hills and valleys substantially distort the airflow by increasing friction between the atmosphere and land mass by acting as a physical block to the flow, deflecting the wind parallel to the range just upstream of the topography, which is known as a barrier jet. This barrier jet can increase the low-level wind by 45%. Wind direction also changes because of the contour of the land. If there is a pass in the mountain range, winds will rush through the pass with considerable speed because of the Bernoulli principle that describes an inverse relationship between speed and pressure. The airflow can remain turbulent and erratic for some distance downwind into the flatter countryside. These conditions are dangerous to ascending and descending airplanes. Cool winds accelerating through mountain gaps have been given regional names. In Central America, examples include the Papagayo wind, the Panama wind, and the Teruano wind. In Europe, similar winds are known as the Bora, Tramontane, and Mistral. When these winds blow over open waters, they increase mixing of the upper layers of the ocean that elevates cool, nutrient-rich waters to the surface, which leads to increased marine life. In mountainous areas, local distortion of the airflow becomes severe. Jagged terrain combines to produce unpredictable flow patterns and turbulence, such as rotors, which can be topped by lenticular clouds. Strong updrafts, downdrafts and eddies develop as the air flows over hills and down valleys. Orographic precipitation occurs on the windward side of mountains and is caused by the rising air motion of a large-scale flow of moist air across the mountain ridge, also known as upslope flow, resulting in adiabatic cooling and condensation. In mountainous parts of the world subjected to relatively consistent winds, a more moist climate usually prevails on the windward side of a mountain than on the leeward or downwind side. Moisture is removed by orographic lift, leaving dry air on the descending and generally warming leeward side where a rain shadow is observed. Winds that flow over mountains down into lower elevations are known as downslope winds. These winds are warm and dry. In Europe, downwind of the Alps, they are known as föhn. In Poland, an example is the Halny Wiatr. In Argentina, the local name for downsloped winds is zonda. In Java, the local name for such winds is koembang. In New Zealand, they are known as the Norwest Arch, and are accompanied by the cloud formation they are named after that has inspired artwork over the years. In the Great Plains of the United States, the winds are known as a chinook. In California, downsloped winds are funneled through mountain passes, which intensify their effect, and examples into Santa Ana and sundowner winds. Wind speeds during downslope wind effect can exceed 160 km per hour.